Yeah.
What about the practice test for exam 3?
No.
Have you done that yet? You haven't done that yet? Anybody have questions about that?
Is the test due tomorrow?
The test is due tomorrow, yes. The practice test is not required. Alright, so we're going to talk about exponential functions today. Anybody know what an exponential function is, or something can explain it? Any ideas? And I'm a little deaf today, so you guys gotta excuse me. Exponential function is when something grows by multiplying. So it's a good example is like population growth, where if you have 2 children, and then each of your 2 children have 2 children, then there would be 4 people. Then if each of them have 2 children, there'd be 8 people, and so on. So we can say that it grows by multiplying instead of just adding a fixed amount. Okay, so for example, if you have your function, say the simple function 2 to the x power. Okay, let's make a table here. Start with -2. Let's do -2, -1, 0, 1, 2, 3. Okay, so if I plug each of those into my function, we have 2 to the -2, 2 to the -1 power, 2 to the 0 power, 2 to the first power, 2 to the second power, 2 to the third power. Now let's see what those are equal to.
So our variable is our exponent?
Your variable is your exponent.
Okay.
So each time you're multiplying by that number 2, however many times. Okay? And that's what you're always going to see in an exponential function, because your variable is in your exponent. That's what makes it exponential.
So, and in -2 exponent, would your answer come out negative, since there are 2 different signs?
Let's do the ones we know first, for sure.
Well,
What we know for sure.
2 to the 0 is 2. 2 to the 0 is actually 0.
No.
No? It's 1?
2 to the 0 is 1. Anything to the 0 power is equal to 1. Always.
To the first is 2.
2 to the first power is just 2. What about 2 to the second power?
4.
4.
And then 8.
8. Okay? Now what about negative exponents? You guys are sitting in front of computers. I need to make some more work. 1/4, right? What happens to negative exponents? They become fractions, right? It doesn't mean you have a negative number. Okay? The number is not negative. The exponent is negative. It'll send that exponent to the denominator and make it positive. So 2 to the -2 is the same as 1/2 to the positive 2 power, which is
1/4.
1/4. I'm going to make you guys Google negative exponents, see what that actually means. 1/4. So 2 to the -1 is the same as 1/2 to the positive 1 power, which is 1/2.
Can you put those powers in the calculator?
You can. You can. Let me pull up my calculator here.
Yes.
You guys got calculators today?
Yeah.
Let's find them.
so enthusiastic today.
My computer just won't slow. My computer's tired. It's having a Monday before. Okay, so if I just do 2 raised to a power of -4, or no, sorry, -2. Anyway, -4, that works the same way. 2 raised to the power of -2, it gives me 0.25, which is 1/4. Okay? So a negative exponent does not create a negative number, it creates a fraction. You guys
Now,
need to remember that.
when I do it,
You're using the minus sign. Syntax error means you're punching in the wrong button.
There's a minus and a negative sign.
No, look what you type there. You do 2 raised to the 2 -4, so you've got an extra 2 there. I'm going to delete that. If you get to syntax error on the calculator, you want to go back and look at what you typed and see what's wrong with it. Okay? Now, the number 2 here is what we're multiplying by. So we're doing 1/4 times 2 is 1/2. 1/2 times 2 is 1. 1 times 2 is 2. 2 times 2 is 4. Each time we're multiplying by 2. 2 here would be called the base of our function. Now, in general, I just used the function 2 to the x power as an example, but in general, okay, we say y equals k times a to the nx power. X is your variable there, so everything else will be replaced by numbers.
So usually there's 2 constants.
They're not necessarily, they don't have to be 2, there can be 2.
Okay.
So you can't have a number multiplied in front, not all the time though.
And what's n?
N would just be a number in front of your x power. So for example, I can make it look like, say, 3. Actually, they'll use parentheses to multiply. And then 4 to the -2x power. Something like that. So my k there would be 3, my a is 4, my n is -2. And x is still my variable.
So say you had a 2 inside there, it would become 1/4 over an exponent of 1/4.
So, wait, hold on.
Just saying that.
Say that again.
No. It would become say your variable is 2.
Okay.
It would become a -4, wouldn't it?
Yes.
And so it'd be an exponent
And
of
then you raise 4
-4.
to the -4 power.
Okay.
Now, what I can think about this as is 4 to the -2, and then all of that raised to the x power. Now, what's 4 to the -2 power?
It's 1/4. 1/8.
It'd be 1/16, right? It's 1 over 4 to the +2
Yeah.
power, which is 1 over 16. So this is the same as 3 times 1/16 to the x power. Okay? So I can go ahead and calculate what that a to the nth power is, and then just raise that to the x power. Now that's not super important that you recognize that, but it can help a little bit just to recognize that those are the same thing. Okay, now there's two types of exponential functions. Okay, you've got a function where your function is getting bigger as x gets bigger. That's called a growth function. So like if you have a population that's growing, that would be an exponential growth function. And what happens when your base, your a to the nth power, is greater than 1? Okay, so if you're multiplying by a number greater than 1, then your function is going to get bigger. Okay, now the graph of that will generally look something like this. It starts off increasing slowly, and then it kind of shoots up as you keep multiplying. Your numbers just get bigger and bigger and bigger. Now the opposite of that is a decay function, where your values are getting smaller. So that's when your base is less than 1. Okay, so every time you're multiplying your function by a value that's less than 1. So this example I have here, 3 times 4 to the negative 2x, that would be a decay function. Because 4 to the negative 2 power is 1/16. Okay, if you keep multiplying by 1/16 over and over again, your numbers are going to keep getting smaller. Every time you're getting a fraction of what you had before.
So is it a safe bet that any negative exponent is going to result in a decay function?
Not necessarily, because if you have a fraction raised to a negative exponent, or a decimal raised to a negative exponent, that would actually, the negative exponent would actually make it a bigger number. Like if you had like, instead of a 4 there, if you had a 0.5 raised to the negative 2 power is 32. Yeah, put in 5, it would work the same way. Okay, so if you've got a combination of a decimal and a negative exponent, those will actually create a bigger number.
Interesting.
Okay, but you really do need to calculate it. Now hold on. The safest thing to do there is to look at the graph. You know, is the graph going upwards or is the graph going downwards? You can also look at your table. Are your values in your table getting bigger or are they getting smaller? Okay, the decay function would actually be the opposite of the growth function. Instead of getting bigger, as x gets bigger, the function is going to get smaller. Now let's talk about graphing these things on the calculator. You really have to be careful about your parentheses on the calculator. Whether you're graphing or if you're just calculating. You guys put parentheses around the entire type after the caret symbol.
So
Okay?
a negative 14 to the second power, you'd have to put negative 14 inside parentheses, right?
You don't want to raise a negative number to a power. You're really going to be dealing with positive numbers here raised to a power. Because if you do a negative number raised to a power, it's gonna jump from positive to negative. It'll be like an oscillating function. And we don't want to go there. Okay? So really I should have said your AN has to be less than 1. It also has to be greater than 0. Okay? You don't want to deal with a negative number as your base.
Less than 1 and greater than 0?
Greater than 0, yeah. So you're not ever going to see that, though. They're not going to do that. So let's say, for example, what was that function I just wrote? Let's just do another one here. Y equals 2 times 4 to the negative 5x.
So that in parentheses right there.
Okay.
Just like that.
To graph that, I would need to do y equals, I'd want to do 2 and then the multiplication symbol, 4 to the power of, parentheses, negative 5x.
Huh.
Okay? Because they'll write it with parentheses around the whole thing here. But really I want to tell the calculator that this is multiplied and this thing is my power. I need to tell it that that's my whole power. Otherwise it'll only think negative 5 is the power, and then it'll just stop and multiply by x. Multiply the whole thing by x. Okay, so you gotta tell it to interpret that correctly. Alright, let's look at some examples here. We're gonna ask them to do. Let's look at the first one here. Now, what did we say we're looking for in an exponential function? The variable is in the exponent, okay? So, letter A, y equals 2x plus 5. That's a linear function. What about B? Y equals x to the 4th minus 4x. No, because there my exponent is 4. My exponent's not a variable. What about C?
Yes.
Yes. What about D?
No.
X squared? No, that's just a quadratic. What about E?
Yes.
Yes. What about F?
No.
1/2 x to the, do you guys see what that says there?
It's E.
E. What is E?
Don't know.
E is a number.
He is the 10th power, right?
What?
To the 10th power. To the 10th power.
Something to the 10th power? What? It means to the 10th power? No, you're thinking something else. Okay, E is a number. Okay? So it's like pi is where you have a number that's attached to a symbol where that symbol always means the same number. Okay? Do you guys have a question?
This is first set this yesterday morning. So
Do you guys see the E button on the calculator? There's an E to the x power because usually you're going to be raising that to a power.
Where's it at?
It's above the ln here. This is E to the x power.
Yeah.
Now on the graphing calculator, you've got a lowercase e above the division symbol. You can also use that. So either one is okay.
what? I'm still kind of confused what it does. Well, what does E represent?
I'll tell you in a second. The actual number it represents is like 2.718281828. It's actually it's an irrational number, so it's not repeating. It looks like it's repeating there, but you're just seeing it's like pi, where it's a number that goes on forever with no repeats and no patterns.
Is there just an E button?
This calculator has it, yours may not. If you only have the E to the X button, then if you want to just spit out the number, just raise it to the first power. Okay. Now you're not actually really going to need to spit out the actual number usually in the course of your homework. You're going to have another power to raise that to. Okay. So if you guys see a lowercase e on there, you can use that, or you can just use the e to the X button.
When you put that in, if it's to that power, you just push the E button? Is that what you're saying?
See when it hits second? So you want to raise it to the second power. So you do second, and then ln. See the ln here? Okay, that gives you e to the x, and then you just put your power, whatever your power is, in parentheses.
And I have to finish the parentheses. And then that.
Okay, now where does this number come from? You know, these constants, if you have a fixed constant, it has to come from somewhere. Like pi comes from the ratio of the circumference of a circle to its diameter. E comes from the expression (1 plus 1 over n to the nth power). Okay? Now, as you keep increasing the value of n,
So continuing getting smaller.
now as the value of n increases, you said that this thing would keep getting smaller? You keep increasing your n?
No, it's because it's plus 1.
And it's raised to the nth power?
Never mind.
This thing actually stops getting bigger. Okay, it reaches what's called a limit in calculus. It gets to a point where you can keep increasing your n, but this thing does not get bigger. It stays the same.
Huh?
Okay? And that number is e. The point where it stops getting bigger, okay, that's your value of e. And we can try it if you guys want to.
Well, okay, now, like on that one problem in here, if you got that, how would you enter that in there?
You wouldn't need to do that. That's just a bogus choice on there.
I mean, would we ever see a problem like
You wouldn't
that?
see one like that, no.
Okay.
That's just that's a goofy one they made up.
Okay.
So if you guys want to try this, like try n as 500 or 1,000 or 10,000. Okay? Let's try it. So if I do 500, 1 plus 1 over 500 raised to the 500th power. Okay? Alright? Let's try 1,000.
And you have to put the whole thing in parentheses?
Type it just like I wrote here, 1 plus 1 over n in parentheses, and then raised to the nth power outside. Okay? So I'm pretty close to that number I wrote down there. You can see the actual number here.
Hey, where is that on mine to raise it to the 500th power?
Okay?
Raise
Now
it
what
to
if I
what?
try 10,000?
To raise it to the 500th power. I looked
Yours
at
is
it.
right.
That's where the E would come in.
Yeah, I don't have a
probably.
caret symbol.
Of course I can't see.
Okay? And I'm at 2.718145927. Okay? And then if you keep increasing that value of n, yes.
I had to raise it to the 12th power.
Y to the x. y to the x and then put in your power after that.
I'm sorry, which one reading?
Y to the x here.
Oh, okay. Thank you.
Okay, if you keep increasing your value of n, your number eventually just stops getting bigger. It lands on that E number, the 2.718281828. Okay, so you can try that. You can increase n as much as you want, but you'll find that number, and then it just stops getting bigger.
So where does it stop?
Okay, it stops at E, that number.
No, I mean, what number do you type in that it would stop at?
Oh, I don't know.
Oh.
Big numbers. You know, probably a million or bigger than that. It's pretty big.
That seems so weird. Why does that happen?
The technical term is called convergence. Like it may technically get bigger, but it would be so far down the decimal line that you would never find it. So you can say that it's effectively the same number within, some arbitrary length of a number.
Okay.
Okay? So it's not physically the same number, but it is, for all intents and purposes, it is the same number.
That makes sense.
I'm going to try a billion here. There we go. Okay.
That's off by one.
Yeah, that's off a little bit. Okay, so it does start getting bigger at that number E. So if you see that E in the problem, that does represent a number, this number. Okay, you want to use the E button on your calculators in order to do those problems. Okay, now let's talk about what is growth versus what is decay. Now the easy way I can do these is to put it on my calculator and look at a table. And then say if it's growth, then your values of y are going to be getting bigger. If it's decay, your values of y are going to be getting smaller. Okay? Or I can look at the base of the function, which is the number raised to the power in front of your x. Okay? So if I want to look at everything in front of my x here, it's raised to the power, I want to say, well, what is that actual number? 3 to the negative 2.1 power. Okay? Okay, 3 to the negative 2.1 is like 0.09955. Okay, so if I take that number and raise it to the x power, would that be growth or decay? Decay, right? Because it's less than 1. So every time you multiply by 0.099, your total value is going to be getting smaller. Now the other way you can think about that is you can look at your graph. Let me find my graphing calculator here. Okay? Now remember, when you put that in the calculator, you've got to put parentheses around the entire power. So I'm going to do 3 raised to the power parentheses negative 2.1x. You've got to tell the calculator that all of that is the power, or else it won't understand. Okay, so I can tell this is decay because as my x values get bigger, my y values are getting smaller. Okay, it looks like like I'm just sort of running into the x-axis here. It's not actually hitting the x-axis, it's just really, really close to it. What's the word for that when I get really, really close to the x-axis? Horizontal asymptote, exactly. So this has a horizontal asymptote at the the x-axis.